Welcome back to part 2 of our live training series here. We're going to be taking a look in this tutorial at finishing off our base map creation process, setting up all of our 2-dimensional and 3-dimensional tables in the calibration file for our K-series engine so it can fire up and run properly on our Infinity. Without further wait, let's jump in so we can check out how to set up our base map. Welcome back to our live training session here. We're going to be taking a look at finishing up our base map creation process. We've started in that last tutorial. So the last tutorial we went over setting up our background details, inputs and outputs, making sure that we have everything configured properly. This tutorial, we're going to be jumping in and taking a look at our 2-dimensional and 3-dimensional table configuration and setup so we have a good starting point to get our engine to fire up and run and begin our calibration process. So let's jump in here and take a look at the very first tab we have in our custom layout that's provided in our training course library. We're going to find that that's going to be our Start tab. So we're going to work our way from our left tab all the way over here to our rightmost tab. And these tabs are laid out in a very specific manner, and the information that's in each page layout is very specific for that task. So the very first tab we have here is called our Start tab. So let's move in here and take a look at working within the tables here, seeing anything we need to change and update. So we have a couple different tables that are going to affect the cranking fuel and the post-start fueling and the warm-up enrichment. So that's going to be factored in here on the Lambda cranking table and the cranking VE table. We also have our ignition map cranking table. So the way this is going to work under cranking conditions below 350 RPM, the Infinity is going to know that we're needing to source an injector pulse width and a spark timing amount to deliver fuel and spark to the engine. And once the engine exceeds that about 350 RPM threshold, it's going to go moving into what's known as the after start, and when the Infinity considers the engine to actually be running. So we have this threshold where we're below a certain RPM, about 350, we're in our cranking mode, then above that we're considered to be in our engine run mode. And we have different things applied and different fueling applied to the engine so that it's going to run appropriately. Now, when we're in cranking conditions, we have our cranking fueling that's determined by our cranking VE table and our cranking Lambda table. Now under cranking conditions, we have the airflow coming into the engine, but it's not going to be the same airflow as when the engine's running. And we really can't accurately determine what that airflow is going to be under cranking conditions with the traditional style volumetric efficiency or mass airflow. So in this situation, we have to use something called a cranking VE. This is going to estimate the airflow coming into the engine under cranking conditions. Then we also have our cranking Lambda table and determine our fuel mass, or what we bring into the engine for fueling. We need to know air mass and target air fuel. So the air mass is coming from our cranking VE values here, and then the target air fuel is coming from our Lambda cranking target air fuel table. So it's going to be air mass divided by target air fuel, gives us an injector pulse width. By going in and lowering down at a given coolant temperature our target air fuel, that's going to give us more cranking fueling. By raising up our target air fuel here, it's going to give us less fueling. If we go in here to our cranking VE, if we raise our cranking VE table values, that's going to give us more fueling under cranking. If we bring down our cranking VE tables, it's going to give us less cranking fuel. Now, generally speaking, the target Lambda here, the target air fuel table, gives us more of a amplitude or more of an effect, giving us more pulse width or less pulse width compared to the cranking VE table. Just at least that's from my experience working with the Infinity. And we're going to run with these default values and test and see how the engine cranks, fires, and runs. The values in both of these tables are really good starting points, so we may not even need to adjust them. The map cranking table here, the ignition crank table, is going to provide the cranking spark timing when we're cranking over the engine, so what the spark timing should be at. 10 degrees is pretty good, so I'm going to leave it at that default value of 10 degrees. If you have a really big cam installed in the engine, let's say you have lock VTEC, you might need to have even higher of a value here. It might need to be something like 15, 20, 25, 30 degrees under cranking conditions in order to get enough cranking torque to get the engine to fire off better, a little bit quicker. So just keep that in mind. Now, if you're finding if you're cranking and you're getting kickback, so you're cranking and the engine's kickbacking, you want to go in and reduce your map cranking ignition timing table values. Again, these are reasonable starting values, so we'll run with what we have in this table. All right, so that's going to lead us into taking a look now at our fuel trim coolant table and Lambda afterstart trim. So once the engine exceeds about 300 to 350 RPM, it's going to consider the engine to be in its running state. And this is where we start to transition from our afterstart time here in our axes. So 0 seconds would be when the engine's still in cranking state, and once it goes above 350 RPM, it's going to be in the after start. So as the engine actually starts to run, it's going to count across here in our axes. So on both of these tables, we'll find that when the engine is running, It's going to be taking a look at the normal air and fuel model that we have with our VE table and our target air fuel, so that's all going to be in play. But what we'll find happens is that we have modifiers to correct when the engine is cold. When the engine is warm, we're going to run our normal VE table values, our normal target air fuel table values. But when the engine's cold, we have to go and compensate for that cold condition. We have what's known as a wall-witting effect, where when we spray fuel into the engine, it doesn't atomize very well. It sticks to the intake valve and the intake track, and each engine cycle, we're not going to be delivering the amount of fuel that we need in the engine. We'll actually run leaner than when the engine is warm, and the air and fuel model will be completely fine to use. We'll find in that cold state, we'll run lean. So we need to overcome the wall-witting effect. We can do two different things. One, we can go in and we can specify a different lambda after start value. So when we crank over the engine and it starts to fire and run, we'll command a richer target mixture. This table value here will go and apply against our normal target lambda table. So if we go in here real quick, we're going to skip ahead and we'll come right back. Thanks for checking out our teaser clip. If you want to see the rest of this video and more than 500 hours of current EFI training we have to offer, make sure you click right here. If you want to go and check out more teaser clips from this training course, click here, and you don't want to miss any of the videos we're going to be releasing on this channel, so make sure you subscribe and click here. Thanks for watching, and I'll see you guys later.